So welcome to podcast 11. It's still going to involve electric motors a little bit, but today we're going to discuss compressed air systems. This will be a more than one part series. But in any case, we're going to cover a little bit of what we did now about just over 2.5 decades ago. So that ended up being my dissertation, which is right here. You'll find a link below, whether you're watching this on YouTube or on MotorDoc AI. In any case, this was called A Novel Approach to Industrial Assessments for Improved Energy, Waste Stream Process, and Reliability. We wrote this and we worked on it. It was a team of industrial engineering students that I was teaching at UIC. Back in 98 and 99. So this was part of the Illinois Food Processing Project. And I'm going to talk about compressed air systems, and I'm going to go and cover one of the examples from a corn miller where we had performed work. Now that'll be interesting because later we'll talk a little bit about steam systems. That'll be probably next, and we'll come back to this. But in any case, that's here. You'll also see MEASUR here and in the background. And then we'll show some other resources that you can access to do this. Now, what I like about MEASUR is it has a lot of capabilities built into it. So you can use some simpler tools than what I use, such as I use electrical signature analysis to do most of my work. So I'm able to see a lot of things. We'll cover this time. Next week we're going to cover ground and neutral currents, and then we'll get back to some other things. But anyways, let's get started. So one of the things is a lot of the resources that we worked on in the 1990s. I was on the fringe part of it, of the compressed air systems, because I was concentrating on Motor Challenge, was the compressed air challenge. So that all of that information is still available. As a matter of fact, and this will be another link that you'll find, that you will find here. And in this section, you will have the tools, which the AirMaster tools are only good on Windows 8 and earlier. So it's not going to work on Windows 10 or 11. Instead, you'll use the MEASUR tool, which is freely available as well, and has all the features, with one or two exceptions, that we had in the AirMaster tool. Tip sheets, which include recommendations and how to do different approaches, some instructions on how to set up the KPI associated with them, and so on. Case studies, applications where they had performed this. Now, some of these come off of the good old-fashioned Save Energy Now program that was done starting in about 2005. I think January 2005 it originally came out. And then there are videos. Now, all of this is free, paid for with tax dollars, so use it and abuse it. This here is just links to the other programs. We'll cover those later. And then technical publications. Now, some of the bigger ones include the source books. And these will go through, for the marketing folks, here you go. Assessment of the market for compressed air efficiency services, guidelines for selecting compressed air system service provider, evaluation of the program, and but this in particular is important. I've clicked on it, so let's see. Too many things running, I guess, again. But in any case, we'll wait for this to download here for a second. But this is the manual put together by a joint team, OEMs, end users, and Oak Ridge National Labs and others. And then it's all been updated through Berkeley Labs. But this is all of the information that you could ask for. 114 pages, all of the tech tips are in there, basically all the resources, recommendations, discussions, things like that. So that is freely available. Definitely will help. It includes tables on how to calculate things. But let's go ahead and get into some real stuff. So the concepts that we had back in the day were to provide tools and procedures for performing audits of compressed air systems used in those plants. BPA, or Bonneville Power Administration, helped develop that AirMaster tool, and now Oak Ridge National Labs has developed MEASUR, which is an open source system. As a matter of fact, if you want to go in and do some of your own modifications, if you have a background in programming, I believe this is done in C, you would go to GitHub, fork off the information they have, or I'm sorry, the program they have there, and then be able to do some development on your own. So in any case, all of it was meant to assist. Now, the models we'll cover in here briefly will assist you in doing things like reducing plant air leaks and coming up with the calculations, the efficiency reduction, and so on, or improvement, I should say, adjusting manual staging, using unload controls, reducing system pressure. Now, if you're able to get the pressure down, you use less energy by default, right? How to sequence compressors, and how to reduce runtime on the equipment. Now, what we've generally found when we go out and we take a look at compressed air systems, they're almost always overloaded. And in a recent case study, I believe I wrote about this in either the newsletter or an article. I ran into a situation where the compressors got so hot, the ball bearings from the motors were eating into, I mean, literally melting the inner and outer race of the bearings. So the challenges that come along with those operations can be pretty significant. And part of the problem with that one was that there were so many air leaks. They didn't have other components that should have been there in the system. There was wet air. They left doors open on the compressors that allowed, because they felt the compressors were running hot, so it bypassed certain things, and just on and on and on and on. In the end, when we took a look at it, and not properly programmed, that was another one. And we're running into a fair amount of that recently as well. We'll cover that in a case study, but in any case, when we start taking a look at our compressed air systems, we'll generally find that there's large opportunities, because it takes, on the electrical side in particular, it takes 9 horsepower to make 1 horsepower, so on average. So that means that my systems are about 10 to 19% efficient. By the time 10 to 15 actually, by the time it gets to where I'm using it. So I'm sitting back here, I've got an air compressor, it's compressing air, it has to go through piping, the piping's leaking, I have filters and everything else, and if those aren't properly maintained, I got pressure drops there, leaks in other locations, everything else. By the time it gets to what I'm using it, I've lost a lot of the energy there. Now, why would we use such an inefficient system? Well, we have equipment, packaging equipment, areas that are that require explosion-proof operations, other hazards where we don't want to use electricity, basically. Now, a lot of cases you can convert things over to electrical systems, and that's usually the best approach. Some of the other things that you can do is start looking at setting up receivers, and also setting up point compressors, like point systems, depending, especially if you have equipment that operates at different pressures. So doing an audit on compressed air, pre-audit, you monitor the power and taking a look at, now I always say you want to monitor plant power overall, let alone the local power, because as you start making improvements, you want to measure and see if the improvements you're making are causing other things to occur. One of the things we found in the study was everything kind of impacts everything else. So when we would try to make a modification in one area, it's possible that another area has to compensate and energy costs actually go up. We found this also, believe it or not, in LED lighting. We're doing LED lighting work, and we were measuring an incoming power, and we put in LED lighting. It's like, why'd the energy cost go up? Well, it's because nobody filtered out all the additional harmonic content, which used energy. So power is monitored. You get electrical bills, understand the electrical rate schedules, things like that. This is how an energy audit is performed. If you are doing this from a maintenance perspective, just look at the kilowatt hours. Don't worry about the rates and everything else. You can use that information and turn over the kilowatt hours if your billing department or accounting cannot provide that information to you for whatever reason, then provide the kilowatt hours change. That is easily then calculated. So general compressed air system components and specifications need to be reviewed. And then you do a plant walkthrough looking at all of the key elements of that compressed air system. Now, what we did at the time is basically almost the equivalent, because we were working on becoming an industrial assessment center at the Energy Resources Center, was basically that. So we had a group of students, 5 students and myself, that went onto the site and went through the plant and kind of looked for blatant opportunities, which were quite easy. So power measurement, you want to basically just record the usage, like several cycles or whatever the operational period is. You get several sets of that data and gives you an idea of what the energy profile is for that equipment. Airflow measurements, when possible, and then pressure measurements, and those can actually be off of any pressure indicators in the system. And then, of course, leak detection. Now, leak detection is usually ultrasound. So you want to use leak detection systems. And then you can both through the leak detection systems, but also by looking at pressure drop, you can make some improvements. So when we took a look at the plant, I'll read through some of this here in a second. The overall efficiency of a typical compressed air system can be as low as 10-15%. I said that already. For instance, several annual energy costs for 1 horsepower of air versus 1 horsepower electric motors, 5 days per week, 2 shifts of operation at 5 cents per kilowatt hour, $19.99, right? Would be $1,165 compressed air versus $195 of electric. Now, we use a lot more than just 1 horsepower. Leaks can be a significant source of wasted energy in industrial systems, sometimes, actually often, wasting 20 to 30% of a compressor's output. We've actually found much higher in some applications. A typical plant that has not been well maintained is likely to have a leak rate equal to 20% of the total compressed air production capacity. On the other hand, a proactive leak detection and repair can reduce leaks to less than 10%. As you can see, you're not going to completely eliminate the compressed air issue. Let's pull up an example here, and I've covered this under the first one, so this is from an existing presentation that we covered before. So when I was talking about pressure drop, This is from that study. If we use 7 cents per kilowatt hour and a $14 demand, which was actually from that site at the time, and at the air compressor, it was putting out 100 psi. At the end of this of their production line, it was at 45 psi. Now, this is a packaging area that was considered explosion proof because of dust, so it was critical that that was there. But at the end of the line, I should be seeing nearly 100 psi. So this is due to leaks, basically. So we take the power measured, which was 220 kilowatts, times 0.5%, 0.005 basically, times the pressure drop, okay, which would have been 55 psi. And then that gives us 60.5 of that 220 kilowatts due to a pressure drop. Now this, by the way, we had 2 compressors there, 2 electric compressors feeding just this system. Both were loaded to 123%. So dropping it, this would have dropped them down to just under 100%, which would have had those machines operating at their best point, meaning their highest point of efficiency. That also came up with a total cost. So the air leaks were costing, meaning the cost to feed air leaking into the air, compressed air is not free, came out to be about $43,500 basically, or almost $44,000. So this was significant. So let's go ahead and talk a little bit more about it. Since air leaks are mostly impossible to see, other means must be used to locate them. The best way is to use, say, an ultrasound meter, which can recognize the high-frequency sounds associated with air leaks. These portable units, compressed air, and ultrasound, basically it's directional. You can go right to them. As a matter of fact, they even now have the systems that will provide a visible indicator on a screen of exactly where. So a visual indicator, just like infrared, that involves a large series of acoustic receivers on the face of the instrument, and then on the other side you would see basically it identifying the location with, I think primarily they use the rainbow type thing, so you get red and yellow and all kinds of other neat colors. But really what you're looking for is that spot that'll tell you exactly where the compressed air leak is coming from. And that's one of the nice things, that it's being directional. Normally, back in the day, we use a parabolic so that it would help identify exactly where we were looking for and just basically walk through. Other things were to, on the weekend or off shift, you would run the compressed air system all the way up, and then when the whole plant was shut down, you'd just walk through with tags and listen for leaks. Simpler method, once you find an area, and we did this too as part of that, was apply soapy water and with a paintbrush to see if there's a leak there. Because now, while the larger leaks make a tremendous amount of noise, and you can find them, and they're more than 50% of the total losses, the other ones are costing you just as well. So if you're at 20% losses, then you want to the 10% of that would be or half would be the audible, loud, and then the other half would be the ones you have to hunt for. Although reliable, this method of course is time consuming. Smoke sticks, candles, foam, manometers, and stethoscopes are also possible. Really, what's the point? I mean, what does an ultrasound meter cost these days? Even if I'm looking at one that's, say, a 15K meter, you're talking about $15,000. You're talking about, you're going to pay for that probably on your first compressed air audit. In addition to, just like what we found with the ESA systems when we were doing this, that's what I had. We went in and we were taking our measurements, and it was like, okay, that pays for this in no time at all. The issue with compressed air found at the Miller were as follows. Air pressure dropped from 110 to 45 psi. Air leaks in the fungi and cooking plant were just huge. Open blow-off valve and one high-pressure 150 psi filter, and that was this one right here. So this was a filter area for their high-pressure air. It was a half-inch opening at 150 psi. Losses through that opening were 561 cubic feet per minute. So that created a demand loss of 120 kW. Now, how did we verify this? Literally, we had somebody at the cogen plant watching the kilowatt meter as we closed the valve, and we watched it drop 120 kW. So the calculations were dead on. This is a little more complex calculation. You can actually get it right out of the book, or right out of the attachment. It's a PDF. So demand was 120 kilowatts times $14 per kilowatt times 12 months. That's your demand cost. 120 kilowatts times 8,000 hours of operation times 7 cents. Now, if we're talking now about a lot of plants, we're talking about 8, 9, 12. One plant we're just looking at was 28 cents per kilowatt hour. I don't know how they got, but anyways, 120 kilowatts times 8,000 hours, that gives me kilowatt hours times that. That's 67,000, so $87,000 right there. Just closing that valve paid for all of the equipment used and the entire study that went well beyond compressed air. I think the total cost for that, including all the hotel and all the other stuff for students and everything else, was like $63,000 for that week, and that included the equipment costs. So $87,000 immediate payback. I mean, shut valve, save $87,000. Come on. Long lengths of flexible air hose. Now, what people don't realize is you get pressure drops across an air hose. You've got air leaking out of the surfaces of the air hose, not just where you make the connections and so on. There were a number of issues identified within the compressed air system at the starch and gluten packaging plant. These included an air pressure drop from 110 to 45 psi. From the compressors to the end of the packaging line. The compressors do not have an opportunity to unload. Basically, the compressors were always on and overloaded. That was one of the things. It went right into the motor side, was the number of times they had to replace motors, repair the compressor, repair lines. Compressed air is also used for bag houses and the need for basically, they had a big need for compressed air strategy. And that's one of the things that the software and the manuals provide that again, are free to put that together. There were 250 horsepower electric motors running on 2 Sullair compressors. During the course of the study, they were found to be overloaded. Okay, and through a basic walkthrough of the compressed air system, several areas were identified. A complete understanding of the demand side of the compressed air system was not identifiable, meaning there were no plans, no drawings left, things like that. Baghouse airlines were not found and traced for air leaks. There was a significant pressure drop. And for the purpose of the study, the compressed air opportunities will focus on, we just focused on just the packaging line, not the other areas, because things were going into the ground, up through the walls, all kinds of stuff. I go through the calculation here, and then we went on. So as we went through, in here we also have how to calculate the dimensions. In the actual manual, they have not just calculations, they actually have a table for the dimensions of the leak. Additional measures that could be taken. Oh, just to give you an idea, off of the air hoses, we came up with a $6,000 worth of, these are just hoses plugged into the wall and not attached to anything. They were just plugged in and left there. Things we found as opportunities: increase the capacity of the receiver. So compressed air receivers mean these are extra tanks elsewhere that could be brought up to pressure to allow the compressors to unload, basically cycle. Balance the load on both compressors. They did have an unbalanced load. Install surge tanks near the bag houses that were served by the compressed system. This reduces the load on the compressors while improving the system line pressure, etc. Then I go into, and I recommend you enjoy reading it, the air leaks at the fungi and cooking plant. First air leak, we identified a single air leak at the bottom end of one of the fungi tanks was a 1/4 inch opening. Using the leak formula, a leak put out 140 CFM, resulting in a 30 kilowatt demand. That one leak, a little hole basically, was a $13,000 per year hole. Second one was the second one was actually that one. And then through the course of looking at everything overall, we found all of the different opportunities, resulting in hundreds of thousands of dollars per year in just compressed air systems. Now, we're not even talking about the steam. Now, considering that steam at this plant was 97% of the overall energy, this was pretty significant. Matter of fact, all of the motors there were primarily pumps and compressors. So we can get rid of this now, and let's talk about the software. So MEASUR allows us to come in and, again, take a look at different opportunities, right? So say we come in and we're looking at that one, and it said, oh, we've got a 60 kilowatt opportunity. Well, how do I tie that to everything else? Well, we can do that in here. I'm going to not do that right now because I want to show you another tool. And in this case, let's take a look at our US EPA greenhouse gas equivalencies. Now, I covered all of these tools in the second and third podcast. So this is basically going back and using that tool. Now, we said we did an improvement, right? So let's go down here. We're going to say kilowatt hours avoided. Now, what's the difference, again, just as a reminder, between kilowatts avoided? Now, this uses a different table off of eGrid, right? So this is going to be the higher value. So if we go off the national average, this is the 0.709. This one down here, hours used, this comes off of eGrid. And what this will do is it will take a look at the national average, which is about 0.495 or 0.498 times the tons, that's tons of CO2 per megawatt hour. So what we're going to do here is we're going to say kilowatt hours avoided. So if we do that correction, and it was coming back here, 120 times 8,000, which would be, let's pull up my handy dandy calculator. Okay. Or not. There we go. Opening up too many of them. So what did I say? That was 120 kilowatts times 8,000, which is 960,000 kilowatt hours. That's a lot. So 960,000 kilowatt hours. So we'll put in 960, 1, 2, 3, or 960 megawatt hours. So we're going to convert that now. It's telling us that's 680 metric tons. Now each metric ton is 2,240 pounds per metric ton. What if I wanted to say this in standard tons? So 750 imperial tons. We could put this into pounds, which I don't want to give that number to management. They'd look at me and say there's no freaking way. So let's go ahead and we'll go with metric tons, which is the common measurement used. Now, what's that the equivalent of? That's saying that we're taking 151 gas-powered vehicles off the road, and that's assuming a vehicle getting about 22 miles per gallon, or 1.7 million miles driven by an average car. This would be the equivalent of 76,000 gallons consumed, or 66,000 gallons of diesel, and which is 9 tanker trucks worth of gas, 132 homes electricity use for 1 year. This is just from a single air leak, and and then here's some of the other equivalency. So it's the equivalent of 11,000 trees planted, or 811 acres of forest, that kind of thing. So in any case, you'll find this here. I will give you the link below, and we will continue now. So let's get us over to MEASUR. Now, MEASUR is kind of cool because on top of everything else, they produced examples. Now, I just updated this, so this is the latest version. If I come in here, let's go ahead and we will find our compressed air system. And we'll let this open up and then we'll go through it. Now, there are calculators and so on in here. New assessment, assessment type, it gives me all the other ones. So compressed air, we're going to just add an assessment. Okay. Oh, got to do a baseline, so I meant to do the example. Go back to this. I'm going to restart it. So anyways, there's an example built into MEASUR. And let me pause for a second because I just updated it and I have a feeling that they moved something. Nope, it's worse. Just as I thought, user error. So anyways, let's go ahead and what we'll do, as I mentioned before, here's everything else. I was just, I just had what is common, well, Navy term, eye fart. So I kind of missed it. I've run some of these assessments before. Just real quick, once you start doing assessments, you can take a look at a summary of all of them here. We'll come back to that later. But let's go ahead, examples. Let's go ahead and just use their compressed air example. We'll give it a second to start up. So here's the pre-setup. So like when I clicked on the button to do everything, it was going to walk me through all of this. This is the this is the system basics. This is the assessment. We'll come back to this in a second. This is a diagram of a general compressed air system. So you can see here compressors, storage, dryer, dry storage, and so on. Now, this actually brings up a good point. One of the big areas, and especially during the winter, for really getting a little extra boost of efficiency out of your compressed air system is bring in cold air. It's more dense. It allows you to compress. It tends to be a little drier, so it reduces the energy a little bit. So let's go back, and we'll start back here. So we'll come back here, and let's just kind of take a look at things. We're going to leave everything the way it is. No, you know what? We're going to change a few things and make it look a little more realistic, because electricity saw a cost of 6 cents per kilowatt hour. Not seeing that these days. So let's go ahead and we will say, now this is in dollars, so 0.09. Demand cost, $5 per kilowatt per month. Yeah, not really seeing that at a lot of companies either. So we're going to, you know what, let's go ahead and we're going to do what I like to do, because tens are always easier to multiply. So we're going to increase some of this impact. So we put this in here, and you'll notice that on the right-hand side, there's some basic help. You can put whatever notes you want in here. Atmospheric pressure. Okay, so this would be, let's say, if you were at, say, 3,300 feet. You notice it drops the pressure. So this is important because, you know, you're going to get a little more air pressure at a higher altitude, but the air is thinner, right? So let's go ahead back here, and we're going to say at 100 feet, let's say. So 50, you'll notice it changed. If I say 0 feet, this would go right back to 14.7. So let's go ahead and we'll leave this at 14.7. Total air storage. So there's ways of doing this. So let's go ahead and click on it. Total capacity, right? So here, this is a way of calculating that value. So we'll go ahead and generate an example, and then we'll use this value here. And it basically what it did, it says, okay, here's the lengths of the pipe. You know, here's the cool part is estimate at first. You know, when you do your comparisons, you're going to compare it on an estimate. Receiver tanks, including sizes, you have the ability to build out the system. And then leak rate calculators based upon the air pressure and discharge time. So that's, yeah. And then, and so on. So this gives you an example here. So let's go ahead, and we've used this. We'll save it. And this will change our value here. Okay, and let's see, multi-compressor system controlled method. So which control methodology is being used? So what we'll do is we'll leave it as cascading pressure. You know what? No, let's change it to pressure sequencer. Target pressure, I think we had it down as 119, so we'll say 120 psi, and we'll allow 5. Okay, so that means that it can go as low as 115, as high as 125 psi. We're going to use the E-grid methodology, which will give us a lower greenhouse gas emissions. Okay, so that's just going to be the way it is, but we're going to go the heck is 6540. Okay, mine, so it's same thing. So that's the emissions for this area region of Illinois updated to now. It's pulling this off the internet. So we'll go there, and then it's going to show a performance profile based upon loading. Let's go ahead, and they basically have a number of compressors built in. So 2-stage, all the same basically. We'll leave those in there. We can get other types as well. So we'll have that description there. And that's so I don't have to change the other stuff. This is, again, if I put in the horsepower, the motor horsepower, I can have it calculate the full load amps and everything else, and then it's also going to calculate my kilowatts for input power. These are the different design details here. That's the controls. Then here's the design, and then performance points, which will be all information that you can get related to the compressor manufacturer. So basically, if I click on this, it's going to show me the details. Now what I want to do is graph all the compressors. So there they are, roughly the same. And then let's click on the operating points. This would be information that that we've entered. Next. So in here it's setting up the number of days. So this is 365 days basically, right? 354 days. Total down days 11. That would be vacations and the like. So 250 weekday days, 104 weekends, and 11 days of basically allowing the compressors to go on vacation to Hawaii. Next would be my system profile. Maybe. There we go. And this would be basically information that I would enter in based upon the operation. Now, different ways of getting this in here, but let's say you put the information in. You can change this to what I believe it's up to a day, right? It's already entered, so I can't change it, because I already have all the data in here. But I can turn it all off, turn it all on, take a look, suggest different things that I want to evaluate. So I can go through and run different evaluations. So let's go ahead next. And then the end uses, that will be basically how it's being used. Right, so basically here we go. And then I can also put in different scenarios. And this will allow me to take a look at all of the different setting up the profiles and everything else. Now, these, of course, are in the manual, so I can add, view, do other things with all of this. Let's get back to where we were here. I can do things like, okay, let's see, let's adjust the auto sequencer. We're going to say adjust it to 1, add primary receiver volume. So these are basically doing certain things to make modifications, right? Improve end use efficiency. So I can come in here and add different things. So changing the leaks, right? So implementation cost, say it's $1,000, send somebody out, identify and reduce the leaks. So what if I said, okay, what would happen if I did $5,000, or maybe not. This is my computer, sorry folks. So in any case, so I can come in there and set up these different opportunities. I can also go through and do different scenarios, and then there we go. And then diagram I mentioned before, and then I can actually do a report based on those different scenarios. Now this basically means I'm using a simulation software to come up with things. So here's my baseline. This one here is reduce air leaks, improve end use efficiency. That was a thing. And then use automatic sequencer, which is, this is part of what I entered in on that first scenario. This would bring us down to a peak demand cost of 243. This one here would just reduce air leaks and not do anything with end use that would end up being $247,000. Simple payback period a month. In both cases, you're looking at a couple of days here and about half a day here, right? Quarter day there. I mean, so these are different ways you can do it. So this goes through and it talks about how the payback was determined and everything else. So in the end, I have some good information. Come on. There we go. Those are the profiles and then graphs that I can use as part of a report. See here, I can download this as an image. I can do different things with it for that report. Okay. And then this basically is a sand key graph that identifies where the energy use is. Okay. And then input summary. I haven't looked at this part before. Okay, so this is all the input data and everything else. So all the information there to run my report, and then I can export the data. There's that sand key. I can do the same thing. I can take an image of that and include that in my thing. So as I begin building up more and more information, that will make the sand key look more complex. And finally, the calculators again. So this would be to look at some basic potential, all the different things I could do. Let's see, airflow conversion, receiver tank storage, system capacity, pipe sizing, velocity in the piping, air leak survey, compressed air pressure reduction, full load current, altitude correction, bleed test. So a couple of these to look at real quick. Let's take a look at compressed air reduction. So let's say 8,760 hours is 24/7. I think we said we were going to call this 10 cents, so let's go ahead and change this to 10 cents. Let's reset it. Let's go ahead and generate an example. Okay, so I guess it wants to leave it at there. So this would be my baseline. So measured, 100 psi, atmospheric pressure, 14.7, compressor power, 200 kilowatts. So that's 1,752,000 kilowatt hours per year. If I come back here and I just drop the pressure by 10 psi, that will drop the consumption to 1.6 million per year. That would give me a reduction of about $6,700 per year at this value here. Now, I'm not sure why this is. There we go. 10 cents. And 10 cents. Okay, so let's go ahead now. That should give me, yeah, there we go. It's fixed it. Bleed test. That's where you put in your total system volume. You put in the test pressure. So let's say, well, we'll go ahead and do the generated example. 100 cubic feet. You have 150 psi at normal pressure. You say, what's it take to go from 150 to 75 psi? 120 minutes in this case. So that would be leaks of 5.3 cubic feet per minute. And then that allows you to get an idea, and then you can put that in and make your corrections and so on. So basically all of these here are meant to provide you basic calculators for doing simple things and simple corrections, and to provide you what's potentially the payback cost. Now, I don't believe in simple payback, so you're going to want to work with accounting to come up with what the hurdle rates are and a bunch of other stuff in order to determine if the financial benefit is good. And we'll talk about that in a future presentation. So in any case, with that, we'll go ahead and end. I appreciate your time again. And next week we're going to talk about what's going on in ground and neutral in our industrial systems and what the potential impact is from an energy and emission standpoint. So thank you very much.